So today we're looking at 6 practice problems, and I tried to include a practice problem that had every kind of force that you will run into in an AP Physics 1 class or your introductory mechanics class in physics. So in this case here, we're going to go ahead, look at the problems, draw the free body diagrams, and we'll talk about the context clues and all that good stuff along the way. Again, if you have questions, just let me know in the chat. So our first problem is a 10-kilogram box is placed on a horizontal surface. Okay, so I know that it's on a flat surface. I have mass. A force of 30 newtons is applied horizontally to the right. Okay, so it gives me information about the force, while a force of 20 newtons is applied horizontally to the left. Okay, draw a free body diagram for the box indicating all the forces acting on it. So first things first, I like to personally start out with a sketch of what's happening here. So we have a box that's on a horizontal or a flat surface. And in this case, it's being pushed essentially 2 different ways. There's going to be 2 different applied forces. You have one to the left and one to the right. We know that because the object has mass, it's going to have the force due to gravity or weight. And because it is placed on a surface, it's also going to have a normal force. Okay. So those are the first couple pieces of information that I have. Now, the next thing that I want to actually do, weight always points down towards the center of the earth, and normal force in this case, it's always perpendicular to the surface. Because our surface is flat, it's going to be at a 90-degree angle, so it should point completely straight. Okay, so for this next part, let's go ahead and actually take that and draw the free body diagram. So I'm going to represent our mass using just a dot. That's often what we use in physics. I mean, just a simple shape. We call it a point mass, and it's supposed to represent the center of mass of the object. So in this case here, I'm going to go ahead and now I need to figure out, what do I want to do? The box is not flying or falling, therefore my y values are going to be balanced, right? So in this case, my normal force will point up and my weight or my force due to gravity will point down. I know that some teachers and professors prefer using W for weight. If that's what your teacher has you doing, that's perfectly fine. Go ahead and stick with what they do with you. I personally like to use F lowercase g because, as my students know, we're now starting to get into work, and work is capital W. So I don't want to mix those two. So in this case here, we can see we have balance. And now we need to go back to the original problem. It says a force of 30 newtons is applied horizontally to the right, and there's a force of 20 newtons applied horizontally to the left. So that means that this one right here is going to be larger than the other force the other way. It should be about 2/3 of the size. And when you're drawing your free body diagrams, it doesn't have to be precise, but you do want to make sure that when someone is viewing your work, they can easily tell that a force is greater than another force. So that is really one of your goals. So in this case, if I wanted to use this and write the net force equation, right, I'm going to go ahead and move to part B. In this case here, we would have our 2 statements. We'd have the net force in the x direction, and we're going to have the net force in the y direction. In the y direction, we said that it's going to be 0. Again, the reason why it's balanced is because it's not flying or falling. That would be the 2 cases where you wouldn't have balance, or it's accelerating vertically, right? Which happens in those cases. But for the x-axis, because we have 30 newtons here, and we have 20 newtons here, and those are the only 2 forces given to us, I know that this system is going to be accelerating. So because of that, I know that this is going to be unbalanced. So in this case, let's go ahead and write the two net force statements. Maybe I need to find a different way to label these two. We're just given two applied forces. I'll call this one 1. I'll call this one 2. There we go. So personally, my preference is always to start with the positive force. And in that case, I'm going to go ahead and write my first statement, which is going to be the positive force, or the positive applied force. So applied force 1. And then I'm going to subtract or take away the negative force, which is the applied force 2. And that will be equal to the mass of the box times the acceleration in the horizontal direction. For our second equation, we're going to go ahead and start with the positive force, which is the normal force pointing up. And then we'll subtract the weight of the object pointing down and set that equal to 0. Now the next part here, we can go ahead and simplify. What's really cool is with this equation, we can solve for a couple of things. We don't really need the connection for y. We can say that normal force, we can expand weight into mass times gravity, which is going to be equal to 0. And then this is a very common relationship that we see in physics. The normal force is equal to the weight of the object, right? It's just opposite in direction. For our other piece though, we can actually solve for the acceleration on the box, which is cool. Because they gave us numbers, we can go ahead and do that. We could also solve for normal force, right? But in this case here, we would go ahead and put in our applied force, which is going to be 30 newtons, minus 20 newtons, is equal to the mass of the block, which we're told is 10 kilograms, times our acceleration. And in this case here, I would just need to divide by mass on both sides. So we have 30 minus 20 is going to be 10 newtons divided by 10 kilograms, which means that the box has an acceleration of positive 1 meters per second squared in the horizontal direction. So I know that with Newton's second law, you can rewrite the statement that net force is equal to mass times acceleration. And there are certain cases where you can solve for acceleration by just writing the net force over mass. That is true. But I think the thing you have to be careful about is that the sum of all forces often implies that there's going to be more than one force that you need to put in that top statement. You can see here, this line is the sum of forces divided by mass. So you can skip ahead to that equation, but you just want to make sure that you're using the information properly. Again, on this side, you could solve for the normal force, which is also the magnitude of the weight. And to do that, we would just take 10 kilograms and multiply it by 9.8 meters per second squared. And that will give us a normal force and a weight of 98 newtons. So we know that this right here is positive 98 newtons, and the weight down here is also going to be negative 98 newtons. The thing that's really interesting about vectors is we can see that force is going to be the combination of mass, which is a scalar value, multiplied by acceleration, which is a vector. So in this case, the really hard switch from kinematics to forces is that students want to make that 9.8 negative, but the negative sign is now associated with the force vector rather than the acceleration. So that's a really big thing to just keep in mind. And it is something that takes a little bit of time to adjust to. But notice that when I calculate, I don't use negative 9.8. I associate the sign at the very end because the vectors that we're talking about here are forces. And so that's where the sign is going to go to indicate the direction of the force. Okay, we finished our first problem. Are there any questions on this first piece before we move on? Again, a good thing to practice is making sure that all of your forces are connected to the same point. Hopefully, if you've been doing this for a while, this feels like review. But if not, we're here to practice. Okay, so we're starting off pretty easy. We're going to slowly work our way into more complex situations. So I hope that you're excited and ready. Let's do it. Okay, so question number 2. A 2-kilogram block is placed on an inclined plane, inclined at 30 degrees to the horizontal. Okay, now we have a ramp. So in this case here, we have mass. We have a inclined plane. Oh, and there's friction. The coefficient of friction between the block and the inclined plane is 0.3. Okay. Draw a free body diagram for the block showing all the forces acting on it. Okay. It's interesting because this problem doesn't innately tell us whether it is static friction or kinetic friction, but we'll work with what we've got. We definitely know which way to draw friction, so that's a place to start. So in this first scenario, I'm going to draw myself a picture. So 30 degrees with respect to the horizontal is going to be, we have the surface here. I'm going to want to increase my plane. I have a block on the plane. So instead of that nice horizontal system, we're now working with a degree of 30. Here we go. In this case, we're going to have a couple of forces. There's always going to be gravity, right? There's always gravity, or the weight of the block pointing down towards the center of the earth. There's going to be the normal force from the ramp or the inclined plane. But again, normal force is always perpendicular to the surface. Therefore, it's going to point up and to the left because our ramp is tilted. Okay, and then for our next one, we know that there's going to be friction. Unless the problem tells you that there's a coefficient of friction or there's friction present, I would most likely assume that it isn't. It's just kind of safer that way. Okay, and with the friction set up here, let me scoot that up. We're going to go ahead and say that it's going to oppose the direction of motion, which this one may not be as straightforward, but think about setting an object down a ramp. It usually wants to move down, right? That would be the direction of motion. Therefore, friction is going to point up along the ramp. Again, because the object is not flying or falling, it's going to be balanced in the y direction. And that's often the place to start because usually it is balanced in y. But let's go ahead and draw what's going on here. Now, at first, let's go ahead. My personal preference whenever I'm working with an inclined plane is to actually create dotted lines to represent my x and y value. See how I'm trying to match that initial diagram that I have, and it does not have to be perfect, but what you're really looking for when you do the setup is that you are creating that 90-degree angle system, right? You want to be able to have that x and y plane be balanced, right? You still want it to represent the horizontal and vertical directions. What's nice about this is it'll allow our forces to exist and not have so many angles. And we only have one force that ends up angled that doesn't work with the direction of the ramp, which is gravity, but that's okay. Okay, so in this setup here, we're going to go ahead and draw some stuff. We're going to add in those forces. Like I said, the first thing is gravity. Always point straight down. And we're going to break that into components in just a second. I'm going to leave all the forces first, and then we'll go back in and change some things. Now we have the normal force, and I'm going to switch colors just so that way I can keep this consistent. So you can see the difference between my X's and my Y's. So I'm going to make my Y's red in this case. So I have my normal force pointing up, and that's positive. As you can see, I've defined. And in this case, we can see FG has an X and a Y component. The Y component will be pointing down, balancing that other piece out. And FGY is going to be negative because it's pointing down. Okay, now for our X components, let's go ahead and look at our friction force, which is going to be in the X direction. Let me grab a different color. So our friction force is going to be pointing up the ramp because it's trying to oppose the direction of motion. Again, we're not sure what kind of friction this is. It could be kinetic or static. In this case, I think I'm going to assume that it is static because it doesn't necessarily tell us that it's moving. It just says that it's placed on there and there's the friction between the block and the plane. Again, how would you determine that? What you want to do is compare the size of the vector between friction and gravity. So if I were to draw the X component of gravity, that would be right here. See that we know to use vector addition. I'm going to go down and then I'm going to go left. The FG, the total magnitude of the vector, is the sum of the components. Therefore, I'm going to make sure that I am using vector math correctly to create that final piece. Otherwise, you may run into the issue of your X component pointing to the right instead of the left, which is a true statement. FG plus FGX would give you that, right? Or minus FGX. But what you want here is the component itself. Now, where is theta? It's going to be located right here. We're always going to take that theta and add it to the component or the force that does not match our new XY system. So I'm going to put it over there. And now we are ready to get started. We have all three forces. We have theta here and we're good to go. The main thing to be mindful of is because our angle is with respect to the y-axis instead of the x, this is where sine and cosine are going to flip. So in this case, sine theta is equal to FGX, because that's our opposite, divided by the magnitude of the force, FG. So you can use your math and trig identities to create the solution. You don't have to memorize these statements. I'd multiply both sides by FG to get that FGX is equal to the magnitude of gravity times sine of theta. And with that in mind, we could do the same thing with the y component. I would use cosine theta. It's going to be equal to adjacent, which is the side touching the origin of the angle, which would be y. And that's going to be FGY divided by FG, the magnitude. And in this case here, this would create our solution of FGY is equal to the magnitude of the force times cosine of theta. So again, if you ever forget this piece, it's okay to just go ahead and take a moment to check in your head, is it sine, is it cosine, and what am I doing, right? Do I have this set up correctly? Now that we have these components, we can go ahead and solve for our net force equations. We can start with our first one being y because it's balanced. Anything that's balanced is always going to be easier to write, in my opinion. So in this case here, we're going to have that the sum of the forces in the y direction, the vertical direction, is equal to 0 because the box is on the ramp. It's not flying or falling. So in this case, I'm going to start with my positive force, which is the normal force. And I'm going to subtract that downward FGY component. But it's no longer the whole thing, right? It's FGY specifically because that is the force being impacted by the angle. And so when we go to expand that, I'll have that the normal force minus m times g times cosine theta, which is the other tricky part, is equal to 0, right? In this case here, we could solve for normal force again, which would be equal to mg cosine theta. What's important to realize here is that the normal force isn't necessarily going to be as long as the magnitude of gravity, right? So this force right here is longer than Fn. And that's okay because normal force is a restoring force. And the key thing to know about it being a restoring force is that it is always trying to balance the system, right? Whatever force is being applied to the surface is just trying to give that same thing back. And so you want to be careful with your normal forces. Don't be lazy with it. Think about what is the force that's actually applying down? What's the sum of downward forces? How do I balance that? Or there may be an upward force that's impacting it, making the normal force smaller, which is also cool. Okay, so when we go ahead and solve for this, we're going to get that the normal force is equal to M, which is 2 kilograms, times G, 9.8 meters per second squared, times cosine of theta. And then this case, cosine of theta is going to be cosine of 30 degrees. If you remember your 30, 60, 90 triangle, you're solid to do that. Okay, so here we go. I'm just using Desmo so that way you can see it on the screen. I'm going to go ahead and plug this in. I got 2 times 9.8 times cosine of 30 degrees. Make sure that your calculator is in degree mode, and you can see that our normal force is going to be equal to 16.97 newtons. Again, we could round because we're given 2 sig figs. Well, technically we're given 1, but that's a lot of rounding. So personally, I think I'm just going to write 16.97. But again, if your teacher is very specific about sig figs, definitely listen to them. I'm pretty lax about that. Oh, let me get rid of the stream. Sorry. Okay, so here we go. In this case, now we can go ahead and look at the x-axis. And in that case, we're going to go ahead and look at f of x. Now, again, it depends. The way that I've drawn this, though, it's balanced. It doesn't show. This problem is worded in a way where it's hard to tell what it is, and maybe I should have made that more clear. But in this case, let's just say that it's balanced. It's kind of cool to have it that way. And the way that I drew my free body diagram, it looks pretty balanced as well. So we'll keep it consistent. So in this case here, I have my positive force and my negative force. I'm going to start with the force of friction, and I'm going to subtract the x component of weight, and I'm going to set that equal to 0. In this case here, we could go ahead and apply, let's expand both of these terms though. So the force of friction is going to be the coefficient of friction times the normal force. And then we could go ahead and subtract Fg, which is going to be m times g times sine theta. Well, you know what's interesting? If we set it equal to m times a, we could see what the acceleration would be. Let's do it. I'm kind of curious. I'm sorry that I'm taking you on this journey with me, but I am kind of curious. Here's the thing. Let's say that the information here is inconclusive. Let's say that because we don't really know, we could determine which one it should be. Oh my gosh, my face is so angry. I am sorry. Why am I angry? I'm angry at the person that wrote this problem. I'm angry at myself, apparently. Okay, so let's say that we want to test this for science. You know, we're scientists. Let's say that hypothetically, we're not sure. We could solve for it, which is super cool. Let's do it. Just like what we did with the last problem. Excuse me. So we have everything we need to solve for it, which is kind of why I'm interested. Here's the thing. If a is equal to 0, we could see. If it's not, then we know that it is accelerating. And this is the thing that sometimes you have to solve. Maybe the question that should have been added at the end of this problem is, does the block slide down the ramp? And that's what we're trying to answer by setting it equal to m times a. So in this case here, we have our coefficient of friction, which is going to be 0.3. Again, it's unitless, times Fn, which we know is 16.97. That's also why I like to keep extra units. I like to keep it so that way we can hold on to as many numbers as possible. Okay, times the mass, which is going to be 2 kilograms, times gravity, the acceleration due to gravity, 9.8, times, let me scoot this over so it's easier for you to see. Okay, times sine theta, which is going to be 30 degrees. Hi, Chris. Okay, and then we're going to set this equal to the mass, which we know is going to be 2 kilograms times AX. Okay, so in this case, let's just go ahead and divide both sides before I throw this in the calculator. So I'm going to divide both sides by the mass. And let's see, is it balanced? Is it not balanced? If it's balanced, it should be 0. If it's not balanced, it'll be a different number. So in this case here, we'll be left with AX is equal to this lovely thing, which is kind of gross. And we're just taking a second to rewrite everything so we can plug this in a calculator once and get our final answer. Wow, I'm still angry. I have to go fix this. Let me see. Oh, it's on the screen. Let me see if I can fix this. Oh my gosh. Okay, I'm back to normal. Apologies. Apologies. I don't know why I was angry. Okay, so here we go. In this case, we want to grab our calculator tool. And I'm going to drag it across. Oh, I'm trying to drag it across the screen, but maybe I can't. Okay, apologies. I'll move it in a second. So right here, what we're going to do, I'm going to use a lot of parentheses because it's just going to help make sure that this comes out correctly. So first things first, whenever I'm using Desmos, I like to just start out with the fraction. So that way it's a little bit easier to do it. So I have 0.3 times 16.97 parentheses minus 2 times 9.8 times sine of 30. And then I want to divide that whole thing by 2. Aha. And we can see that there actually is a slight acceleration. So I'm glad that we did this. So in this case here, we're going to see that the acceleration is going to be negative 2.3545. So I'll just say approximately negative 2.35 meters per second squared. Now, what does this tell us about the box's motion? Well, if positive is up the ramp, based on how I set up my system, then that means that the box is going to be, in fact, moving down the ramp. So looking back at my initial picture, there is an acceleration in the x direction. Therefore, it is going to be moving downward. And that lets me know that the type of friction that we have in this problem, it is kinetic. So this is kinetic friction. And if the block was at rest, then it wouldn't be. Let me move the calculator out of the way. That's really cool. So if you're unsure if a system is balanced or not, this is a really great way to tackle the problem. It does require a little bit extra work, but you can get it to be 0. Okay. Any comments, questions, concerns before we move on, other than Chris saying hi? Oh my gosh, there's so many of you here. Congratulations on spending your weekend studying physics. You're becoming instantly smarter. Hello. I can see your chat comments still. Don't worry. But yeah, this is awesome. It's so great to have you here. This will record and it'll also share. I know some people have practice today, so just tell them, when they get a chance to watch the video. And if you haven't already and you hopped in late, welcome all the people. There is a pinned doc that you can copy and paste. You can either type on it or you could print it. Do what you want. I don't know. I don't have an iPad, but I know some of you do. So feel free to do whatever you'd like with the digital copy. You can download it as an PDF as well. Yeah. In this case, question 3. A car of mass 1,000 kilograms is moving on a horizontal road with a constant velocity of 20 meters per second. Draw a free body diagram for the car, indicating all forces acting on it. Ooh, I like this one. Okay, so this one I don't know if we're necessarily going to be able to solve for a lot, but it's still a good question because it brings up a good point of hidden forces, where there's not necessarily a force that you expect to see, but it's going to be there. So in this case, we're going to look at some practice problems here. First things first, we have a car on a road. Now, you know that I have the best drawing of all time. And so, wow. Just wow. Look at the car. Oh my gosh, why is the car hitting the ground? Don't even worry about that. Don't even worry about the car hitting the ground. It's fine. It's fine. It's artistic liberties, We are told that it's moving with a constant velocity of 20 meters per second. Because it doesn't give us a sign, I'm assuming that it's positive. So it's moving to the right. And we have that it's on a flat surface. Okay. So in this case here, when I'm thinking about forces, there's always gravity or the weight of the car. Pointing straight down. We also have the normal force from the road. Pointing up. We have the applied force from the car's engine or the thrust force, depending on the class or textbook. That's pushing the car forward. And then in order for it to be balanced, though, we'd actually need a force going backwards, which the reason why cars can move forward is because of friction. So we're going to have some kinetic friction. Pointing backwards. The other option would be to just completely ignore the horizontal forces, like the car's just in cruise control, which is a possibility, but even then the engine's still working. Okay, so in this problem, we're going to go ahead and start with our dot. We're going to have the applied force to the right because, again, applied force is always going to match the direction of motion. And then in response, we're going to have the friction force balancing that, pointing back. And the reason why this needs to balance it is because of the fact that we have a constant velocity. That means that there's no acceleration in the x direction. Also, I've never seen a flying car, but I know that they kind of exist. There's some weird stuff happening in tech. But in this case, we would have FG, or the weight pointing down, and we would have the normal force pointing up. And boom, this one's another nice and simple one. The tricky thing here is the X components, the forces there to actually create a balanced system. Again, you could probably argue that cruise control would result in none, but you do need friction in order to move, especially as a car. If your car runs out of treads on your tire, it's kind of scary to drive. So in this case here, we'd have a nice dually balanced system. Let's see, we'd have balanced for f of x, and we would also have balanced for f of y. And in this case right here, we would go ahead and set up our net force equations. Again, I'm always going to start positive. So I'm going to start with the applied force or the thrust force from the car's engine, which is pushing the car forward. And that is being balanced out by the force of kinetic friction that is helping the car connect to the road. Again, they're at a constant velocity, so I know that those values should be equal to the same thing. Now, the applied force, we don't necessarily have values for either of these, but we could still write their general equations. In this case, because I know it's going to be kinetic friction, I'm going to write mu k, and then I'm going to multiply that by the normal force, and that's equal to 0. Okay, on the y side, we would have the normal force minus the force of gravity, or the weight of the object, is equal to 0. And in this case here, we would have the normal force minus m times g is equal to 0. So therefore, the normal force is equal to m times g. And we could get that value as well. We would go ahead and multiply 1,000 kilograms times 9.8 meters per second squared. And in this case here, that would give us, grab my calculator really quick. Yeah, okay. 9,800 newtons. Sorry, let me scroll up. Which means that roads are really strong. Now, in comparison, the human body can survive approximately 4,000 newtons, just your random fact of the day. So that is why most people wouldn't survive like a car running over them. You know, just your fact. In this case here, we would go ahead, we could take this value and plug it in up here. The applied force minus mu k mg is equal to 0. And what's cool about this is we would be able to solve for the applied force if we knew what the coefficient of friction between the road and the car tires were. Yeah, there we go. That's our next problem. Any questions here? Again, if we had a coefficient of friction, we could solve for the force of the engine. Okay, let's go ahead and move on. So in our next problem, we're going to be looking at tension force, which is good. We haven't looked at a problem with tension yet. We have 2 more forces coming up. We have tension in this problem, and then we also have a final question that has air resistance in it, which I know is usually ignored, but I thought it was important to do one together because we don't have a lot of practice with it. Okay, so a 5 Newton weight is suspended by 2 ropes as shown in the diagram below. Yeah, we're going to make the diagram. One rope makes an angle of 30 degrees with the horizontal, and the other rope makes an angle of 60 degrees with the horizontal. Draw a free body diagram for the weight, showing all the forces acting on it. Okay, you're so lucky because you have me, the greatest artist ever, Miss Phys, and I'm here to help you out. So in this case, let's go ahead and set it up. Man, if you were looking for like a boss battle, we have 2 different angles, although they are 30, 60, 90 triangles, which is kind of nice. Okay, let me just go in here really quick and highlight some things. Okay, so we're given weight instead of mass, which is important. We're going to need to work with that. The first rope, I'm going to call it T1, makes an angle of 30 degrees. And let me switch colors so I can keep track of these ideas. The other rope, we'll call it T2, makes an angle of 60 degrees with the horizontal. Okay, and then we want to draw a free body diagram for the weight. Okay, so first things first, I'm going to set up suspended. Gives me the idea that it's hanging in the air. Okay, so our first rope, let's add our little mass, 60. Okay, we're calling this T2, and we're calling this one T1. A couple things. The first thing that we know is that it's going to have gravity always. In fact, we're already given the weight, right? And it's going to point down. We do know that we have tension. So we have two tension forces, and one points up to the left and one points up to the right. Let's make it less slanted, right? So we have two tension forces going on here. I should have put the number 2. That's okay. I'll say tensions. Okay, and then I think that's it, honestly, right? Because here's the thing. Now you might be saying, but Miss Phys, it's touching the ceiling. What about the normal force? That's a great question. Because the tension is attached to the mass, that's the thing that we care about. We only care about normal force, like the car on the ground, when the surface is touching that object. So if it's not making direct contact, then because it's a contact force, we're not worried about it. The force that we experience from the wall, it's matched by the tension force. So we just have two tensions and we have gravity. Nice and easy peasy, right? Yeah, but there's lots of angles, but it's not too bad. So let's do it. Let's start out by drawing just the general setup first, and then let's go deeper into it. Okay, so in this first case here, we're going to go ahead and have, our, okay. You know what I'm going to do? I'm going to set up my y-axis and my x-axis again. Whenever I'm working with a system with angles, I just like to give myself a blueprint, right? Make sure that you get that nice crisp 90-degree angle, and it's a little bit easier to look at your components later too. So I have positive y up. I'm going to have positive x to the right. So in this case here, let's go ahead and do it. So our first case is going to be looking at the x component. So in this case here, there's one force that's nice and clean and simple, which is going to be gravity. Let's start there. In this case, we have a problem with angles, but gravity is not going to be tilted, right? Straight up and down is our system for this problem. Now, why don't we want to tilt it? Well, because there's two different angles. It doesn't really make sense, and we're not going to gain anything from doing it. So in this case, we have two forces. I'm going to draw T1 this way. And I want to make sure to have that angle of 30 degrees in there. And then I'm going to draw T2 this way. But I need to be careful. Okay. The reason why I would need to be careful is because I'm trying to set myself up for success. And I know that may not be exactly 60 degrees, but that's okay. Because here's the thing. I need to make sure that the y components are balanced because it's a hanging mass. So it's going to be staying in place. And so because of that, I actually want to make sure that the sum of these two y components right here, this is T1y, and then this y component, T2y, I want to make sure that my FG is equal and opposite to the magnitude of those two components, right? So in this case, I'm going to make sure that I draw that FG vector to be greater. And this is something that I think students often will skip in their work, but it really does make a difference. One, in the visual presentation of what you're doing. And two, it also helps with trying to figure out what it is that you want to do for your net force equation, right? So hopefully you can kind of see my FG is about double each of the tension y components. Okay. In this case, now we want to also look at the x components, which means, well, to be honest, I'm assuming that these will balance, but who knows? You know what? Who knows? I know it's not falling or flying. Although, to be honest, I think it is. I think it's balanced. So we have T1x, which is interesting because it's positive. It points to the right. And we have T2x, which is negative because it points to the left. So in that case there, we can see a system like so. Once you realize there's a lot of stuff going on here, it's a lot of work. Okay, so really quickly, because we have our angles both drawn with respect to the x-axis, really quickly, our cosine theta is going to be equal to T1x divided by the tension. Let me just do it in general. I'll just do Tx divided by T. That way we can keep it general to both. And then cosine, or that means that sine theta is going to be Ty divided by T. So in this case here, that will kind of guide us for what we want to use. That means that Tx is going to be equal to T cosine theta. And it also tells us that Ty is going to be T sine theta. This works for both of them, so I just wrote a general statement. Okay, so now that we have this, we can write our net force equations. Yeah, I'm going to assume that both these systems are balanced, and then let's see if it works out. The reason for thinking that is if you're hanging a sign by ropes, I'm going to assume that the sign is going to be steady, right? Even hanging a weight suspended by two ropes, that seems even more dangerous. You would want that system to be balanced. So in this case here, the last thing that I do need to keep in mind, well, I was going to say we might want to solve for mass in certain cases, but if the system is balanced, we don't necessarily need mass. Okay. So in our first setup, I'm going to say that they're balanced. So our fx value is equal to 0. And I'm going to always start with my positive component. So it's going to be T1x minus T2x is equal to 0. And then in my second scenario, I'm going to say, well, we can expand this a little bit. T1 times cosine theta minus T2 cosine theta is equal to 0. And our other statement, we're going to have that they are also balanced. Therefore, our net force in the y direction is going to be equal to 0. And in this case here, I'm going to have three forces. I have the positives always, T1y plus T2y minus f of g is equal to 0. Okay, and then expanding that, I'm going to get T1 times sine theta plus T2 sine theta minus mg is equal to 0. Now, if we were given the tensions, we could go ahead and we could solve that. We do have the angles, but what you could do at this point really is you can use the idea that pops up in physics and also math, which is systems of equations. So we have two unknowns. We don't know tension 1 and we don't know tension 2. And I'm going to need more space for this problem. So let me scoot down question 5 really quick. See if it'll let me do it. Perfect. Okay. So this is going to be a journey. When I say in class you want to use a system of equations, I mean that just like in math where you would solve for one variable and then plug it into the other, we want to do the same thing here, right? They don't cancel. We can't just stack them and multiply them by a value because we're working with cosine and sine. And we can't just set them equal to each other. This is a big red flag that I see with students. You can't just set these equal to each other because they're both equal to 0. Because we're working with vector math, they are not equivalent statements, right? We can only solve for equivalent magnitudes. And so that really is a game changer because it limits the way that you can work with these problems. But what we can do is we can work around it, right? So we can say that we can solve for T1 as a function of T2 or the other way around, whatever your preference is. So T1 cosine theta is equal to T2 cosine theta And in this case here, if I wanted to solve for T1, I would just divide both sides by cosine. And then at that point, you really do need to plug in our values. Maybe I should call them theta 1 and theta 2. What do you think? Sometimes I'll use a different notation. Okay, so this would be equal to T2 cosine theta 2 divided by cosine theta 1, where one of those is 30 degrees and one of them is 60 degrees. Okay, now what can I do with this? I can substitute it in for T1 in the other problem as a function of T2. So in this case, I would get T2 cosine theta 2, but then sine theta 1 over cosine theta 1 is actually just tangent plus T2 sine theta 2 minus mg equals 0, right? And then from here, you could go ahead and isolate T2. And then you could solve for that component by dividing both sides by that variable. By adding mg to the other side, and then we're going to divide by this lovely set of variables. You know? And if you were ever wondering, what the heck are they doing in physics? You know? You realize how far you've come in the class because you're working with stuff like this and you're able to do it, which is awesome. So in this case here, we'll divide both sides by this statement. And if you prefer to plug in the numbers already, you're always more than welcome to. Okay. And this lovely statement right here. May be a solution that you're asked to find. What is the tension in object 2? In the rope, the second rope, right? And at that point, you could plug in mg, we know is 5 newtons. Divided by cosine of theta 2 is going to be, let me label it over here, 60 degrees. And theta 1 is 30 degrees. Okay, just for reference. So cosine of 60 times tangent of 30 degrees plus sine of 60 degrees. And then in this case here, we would pull out our calculator because that is a lot. That is for sure a lot. Let me scoot it over so you can still see it. And let's pull up Desmos. So in this case here, I'm going to first press the divide button so that way I have a nice fraction. Oh, populated on the wrong screen. So in this case here, I would have 5 divided by, and then I'm going to have cosine of 60 degrees times tangent of 30 degrees plus sine of 60 degrees use parentheses around the argument of cosine. Okay, there we go. And we would get that T2 is going to be 4.33 newtons. Now, could you leave it in its general form? You 100% could. But the thing is, then it's a lot more complicated to plug it back in. So in this case here, I can now plug this into my original statement. The original equation that we made, T1 is equal to T2, which is going to be 4.33 newtons times cosine of theta 2. Get rid of my calculator really quick, which is going to be cosine of 60 degrees divided by cosine of 30 degrees. And then I could also solve for T1 because FG was already given. So what we're really working with is the other two tension forces. So bringing back my calculator, we're going to go ahead and plug this in. I get my denominator. I have 4.33 times cosine of 60. And I'm going to divide that by cosine of 30 to get an answer of 2.499, so approximately 2.5 newtons. And there you go. We did it. We have solved for both the tensions that we're missing using what we know about the force components and the weight of the object. Look at all that work. That's probably the most challenging problem on here, by the way. So if you got it, you're good. Okay. For our next one, we're going to go ahead and look at a 50 kilogram crate that is being pulled along a horizontal surface of 200 newtons applied at an angle of 45 degrees above the horizontal. So in this case, we are going to use the coefficient of friction between the crate and the surface is 0.2. And we want to draw the free body diagram for the crate indicating all forces. Okay, I think this is going to be another problem we're going to solve for the horizontal component of acceleration to see if it's balanced or not. So let's go ahead and practice. Give me 1 second. How did I get angry again, everybody? I promise I am not an angry person. Like, I'm just being overwhelmed right now. Apologies if you see the screen set up. Okay, so there we go. I'm back to normal. I noticed that my VTuber model always goes like angry face whenever I'm like deeply focused or like deep in thought. And I promise I'm not angry. I'm just like thinking. So let's go ahead and do this next problem. A couple of things. We have mass, we have an applied force, and we're working on a surface that is, oh, it looks like our surface is flat, but the applied force is at an angle. Beautiful. Okay, let's do it. Coffee break. Okay. In this case, I'm going to start out by drawing it. Let's do it. So in our first case, I'm going to draw my diagram. Again, I love to use a simple diagram to really guide what I want to do for my free body diagram. It takes like 30 seconds and it's definitely worth the time. Okay, it looks like our force is going to be 200 newtons at an angle of 45 degrees above the horizontal. It's positive. Therefore, to have a dual positive force, I'm going to go for this system right here. It's up and to the right. So I have a 45 degree angle, and this is my force applied. And then I'm told that there is friction on the surface. And the way that I like to denote that there's friction on the surface actually is to give myself an uneven ground and the box. And what that lets me know is that there's going to be some stuff going on there. Okay, I think that's it though. That's all we need. Let's do it. So forces that are present here, always gravity and always straight down. Towards the center of the earth, we have the normal force that's pointing straight up because our surface is flat on the horizontal. It's just our force that's now angled. And in this case here, we are going to have that applied force. And it's going to point to the right at a 45-degree angle. Okay, there we go. With respect to the horizontal. Maybe I should give that little dotted line. Okay, that's everything that we need though. Oh, of course not. There's friction. See, this is why my diagram helps me remember what I want to do. I am getting the sentiment that it is moving though. Just in my heart of hearts, I feel like it's moving. Okay, it's on the surface though. So we do know a couple of things. I do know that my y component is going to be balanced, right? Because in order for it to experience friction from the ground, that means it's staying on the ground. So just thoughts. And then in the x direction, we're really not sure. That's what we're trying to figure out. So because I'm not 100% sure, in this case, I'm going to go with m times ax. And then if we get an acceleration that isn't 0, I would say it's unbalanced. So in this case here, let's draw it. I'm going to have, ooh, I love this problem. This is such a good talk. Okay, so I'm actually going to start with the applied force. So because we have forces happening at an angle, I'm going to also do my little sketch. Well, I think it's kind of okay. Hopefully I did 45 degrees. It's kind of 45. It's kind of giving 45. Okay, so 45 degrees, and this is the F applied. In this case here, I'm going to also go ahead and add a couple more forces. I'm going to add my normal force first. And notice I'm not going to make it super tall. And I also want to think about the fact that there is an upward component, right, from here. Because again, when I draw my balanced force for the y component, the gravity needs to be the y component plus the normal force. Therefore, I want to do that length, those two lengths combined when I'm drawing the force of gravity pointing downwards. Again, it's such a simple thing, but it is really impactful and it does show that you understand what's happening in the problem. If you want to impress your physics teacher or professor, this is definitely a skill to practice and work on because it does make the difference and it's more physically accurate. Okay, now for the x direction, if we're going to assume it's being pulled to the right, that means that friction is an oppositional force, so it should point in the opposite direction to the left. Yeah, we're not sure what kind of friction we're working with right now. I just am going to label the direction that it's in, and I know that it is opposite the direction of potential motion, right? But I think it is moving. And so F applied X. With that in mind, I do think I'm going to make this a little bit shorter. Why is it going the opposite direction? It does not want to be shorter. There we go. Okay. So in this case, let's go ahead and see if that's actually true. First things first, let's write our two net force equations. So we have the normal force plus, the force applied y component minus the weight of the object is equal to 0. In this case here, sorry, my cat is trying to eat my breakfast right now. What in the world is happening? In this case here, I have the normal force plus the applied force, and that's going to be sine of theta minus m times g is equal to 0. And then on the other side, I'm going to go ahead and set up my x, and this is going to be F applied x minus the force of friction, and I'm going to set equal to m times a, because again, I think it may be unbalanced. In this case, I have the applied force times cosine of theta minus uk times fn which is equal to m times ax. So there's our two force statements here. Now, in order to solve for acceleration, we do need to solve for normal force. So that's going to be my first target here. So my normal force is going to be equal to, I want to move the other stuff to the other side. So normal force is going to be equal to the weight of the object minus the applied force times sine of theta. Plugging those numbers in, I have 50 kilograms times 9.8 meters per second squared minus 200 newtons times sine of 45 degrees. And then bringing back up my calculator, let me scoot this over so we can keep it on the screen. So I have 50 times 9.8 minus 200 times sine of 45 degrees. And there we're going to get the answer that our normal force is going to be equal to 300 and, oh wait, no, I subtracted them. Okay. So we're going to get 348.58 newtons. Okay. Now that I have this, I can plug it into the other equation to get my acceleration. Really quickly, I'm going to take this moment to divide by mass just to get my general equation simplified in the beginning. Okay, there we go. So that'd be my general solution, and then let's go ahead and solve for it. So in this case here, I would go ahead and divide. So we're going to have 200 newtons times cosine of 45 degrees minus our coefficient of friction, which is 0.2, I believe. Yep. Times our normal force, 348.58 newtons. And then I'm going to go ahead and divide that by the mass of the object, which is 50 kilograms. And that will give me my horizontal acceleration. Okay, so with that in mind, we could go ahead and calculate. Let me scoot it over so we keep it on the screen. And in this case here, set up that fraction. We got 200 newtons times cosine of 45 degrees. And then we're going to go ahead and subtract our 0.2 times 348.58. And then I'm going to divide that value by 50. And that gives me an acceleration of 1.43. meters per second squared. Okay, we did it. So there's one last problem, I think, and then we are done, everybody. Very exciting. Now, the last problem that I wanted to include, though, for today is a problem with air resistance, because we know that it's important, but we often don't talk about it. But what if it is there? There are some problems in your physics classes where there will occasionally be air resistance. So in this case, a 2 kilogram object is dropped from rest from a height of 50 meters. Air resistance is present, exerting a force of 100 newtons upwards when the object is falling. So we're given some information there. 100 newtons upwards when the object is falling, air resistance. Draw a free body diagram for the object at the instant it is dropped, indicating all forces acting on it. Okay. So in this case here, we have an object that is falling from rest, but that means it's going to be accelerating, right? This is kind of like a free fall problem. So in this case, it's being dropped off a cliff, let's say. We know it's going to fall down sometime later, right? And it's an initial height of 50 meters. Okay, so in this problem here, we are going to look at the forces. There are 2 forces, right? During free fall, there's always going to be gravity pointing downwards. But in this case, we also have air resistance pointing back up because it's an oppositional force like friction. So it's always going to pose the direction of motion. So what are we going to do with this? Now, we can actually use this information to solve for the vertical acceleration and then turn it into a kinematics problem and solve for the time that it takes to hit the ground, which is kind of cool. Let's do it. So in this case here, really quickly, our free body diagram for our object, we're going to have FG pointing down due to the weight, and we're going to have air resistance pointing up. Now, innately, I'm going to assume that air resistance is smaller than the force of gravity because in order for the object to fall, it's going to need to move downwards, right? Like my net acceleration should be down. So because of that, I'm going to assume that that is not the case. Also, we know 2 times 9.8 is going to be greater than 10. Okay, so first things first, let's write our net force equation. We have just the y-axis, and that's going to be the mass of the object times the vertical acceleration. Again, it's not just g in this case, and we can see that because we're going to have the air resistance minus mg is equal to m times ay. And so in this case, we can solve for our new vertical acceleration by dividing by m. So I'm going to get the force of the air resistance minus the weight divided by mass is equal to my vertical acceleration. So if you ever had a problem where there's air resistance and you need to figure out what's the new acceleration of the falling object, this is exactly what you do. You'd actually start with the free body diagram and then see the connection between acceleration. In this case here, let's solve for it. Let's do it. So in this case, I'm going to get the force of the air resistance is going to be 10 newtons. And I'm going to subtract 2 kilograms times 9.8. Meters per second squared. And then we're going to go ahead and divide that by the mass of the object, which is 2 kilograms, to get our vertical acceleration. Now, bringing back our calculator, apologies, we're going to go ahead and apply it. So in this case here, I'm going to calculate by doing 10 minus 2 times 9.8. And then I'm going to go ahead and divide that by 2. And I get an answer of negative 4.8, which is good, right? In this case, because there's air resistance, I would expect our vertical acceleration to decrease because there's now something that's opposing the acceleration due to gravity. So you should expect an answer that is less than 9.8. But now that we have this, you can actually use the kinematics equation to solve for the time that it'd take to hit the ground, right? So in this case, we'd have delta y is equal to v naught t plus 1/2 ay t squared. Again, your teacher might use 1/2 g t squared, but because it's not g, I'm just going to be more generic. Okay, So in this case here, we know that our delta y, because we're moving downwards, is going to be negative 50 meters. My initial velocity is 0, so this term is 0. And then I have 1/2 times negative 4.8 meters per second squared times t squared. Okay. Half of negative 4.8 is going to be negative 2.4. And then I just need to divide both sides by the negative. Again, I have a bunch of videos and I just came out with one about free fall. It is really important to make sure that you check the sign of your displacement because we're moving down. That's going to be negative displacement. And in this case here, we would go ahead and solve by dividing those two values, right? So we got negative 50 divided by negative 2.4, and that's going to give us a time squared equal to 20.8333 repeating second squared, which is equal to t squared. And in order to solve for this, our last step is going to be to square root both sides to just get t. So in my calculator over here, oh, apologies, let me scoot that over so you can see. In my calculator here, what I'm going to do is I'm going to take that value, square root it, and that is going to give me a time of 4.56 seconds approximately for the object to hit the ground. Now that is going to be more time than what you would expect for something that's falling due to gravity, which makes sense because our acceleration is now smaller, so it should take more time. Yeah, so this is how you could use a free body diagram, get an acceleration, and then connect that idea back to your kinematics equations to solve. Yeah, which is really cool. I think it's a really good review. I mean, this is stuff that you probably haven't touched since last semester, but it still impacts what you do in semester 2 in physics. So it is really helpful to just practice that review and seeing how you can use the different net force equations from those free body diagrams to solve problems. And again, hopefully it also help you address what are some things that you want to clarify or tighten up on your free body diagrams to make them really clear for your teacher or for your professor. But yeah, thank you so much for hanging out with me this morning. I hope that it helped.